day 3 of the workshop. I think today we're also going to have a lot of interrelated talks on the ideas of molecular simulation, which have come up a lot in the last couple days as well. We'll start with our first speaker for the day. Rafa is coming from MIT.
Thanks so much, Aditi, and Jennifer for having me. Thanks so much for organizing. I think all the talks have been amazing. I think I'm worried I'm going to break the track record, but the talks so far have been really, really fantastic. So thanks so much for organizing. And I think this maybe doesn't need a lot of introduction, maybe, but while people's coffees kick in. Why are we doing this, right? Like, why am I sort of? I'm in material science, and at the end of the day, it takes about 20 years, and somebody has an idea in the lab making something till it makes it to market. It takes about 20 years. And if you look at the 2050 climate goals, well, that means we have actually 6 years, right? Because it's going to take 20 to actually scale up materials. And this is energy storage, energy generation, remediation, agriculture, plastics. What are we going to do with plastics, right? We make 100 million tons of plastics that essentially go into the environment. So there's all these things that sort of require materials innovations. Like how do we solve the design problem for materials? How do we find sort of the chemical or the material that really solves this complex optimization problem? And then we've got all these tools that have been amazing, and problems that seem completely intractable turn out to be not that hard, right? Like, and which problems were hard and which problems were easy, I think has been, I think we have good intuitions about those, right? Go was supposed to be a million times harder than chess, and then it turned out that it was sort of solvable with reinforcement learning, over a decade ago. Image generation, and then we've heard a lot about data-driven protein folding or protein structure prediction, right? So even something that is more on the sort of curiosity-driven science has been sort of surprisingly tractable. And this is through an obvious combinations of like we all know, just big GPUs that we cannot afford anymore, and algorithms and data that we also don't have. So in addition to sort of using ChatGPT for writing cover letters, I'm never writing a cover letter again. And I'm hoping you folks are not reading cover letters ever again, because I don't know how we're going to interface LLMs for writing and reading. I want this for materials, right? Like how do we sort of utilize these abilities for materials discovery? And interestingly, one of the differences, and I think this has been sort of in the air also in the protein design discussion, we want to do better than the best human, which is not the same as what we ask for GPT or for diffusion models, which is just come up with okay images, right? They don't need to be better than the best. They just need to be in distribution for whatever images we're used to seeing, right? So it's somewhat different. And then we're never going to have as much data as sort of the semi-supervised tools in language or in images. So hopefully there is some sort of inductive bias that we can use, but even that is contentious, right? So it hopefully helps, but it's not 100% clear that the inductive bias and the laws of physics are going to help us. And then my last comment would be, and then goes back to I think a conversations we've had and we've heard, what distribution are we trying to draw from when we do design? It's also very unclear. Right? So, proteins are maybe a smoother, more natural distribution than molecules. And maybe molecules and crystals are sort of materials are maybe the same sort of level of difficulty. So in this context, and coming from simulation, sort of the group sort of lives in this spectrum, right? When sometimes we have a collaborator that dumps 100 data points on us and tries, hey, what should we do now? And that's sort of very black boxy and more on the just surrogate modeling part of the world. And sometimes we do sort of high throughput simulations where there is a simulator that we trust. We just call it 1,000,000 times. By the millionth time, we probably don't need to call it anymore. We can make a surrogate for that, and we operate in sort of physics-based simulations. And in between is, I think, where sort of, and Aditi will also describe really, really cool stuff in sort of this, how do we combine or move along this axis of either injecting some learning into physics-based functions, or how do we inject inductive biases and reasoning in more sort of black box models. And this boils down to, or something I've been excited, and I think a lot of the community has been excited about. Sort of, it turns out we have differentiable programming, the same thing that powers deep neural networks, turns out to make accessible derivatives that have been of interest in molecular simulations and power both learning and optimization in this intertwined way in molecular simulations. So we and many other people are sort of trying to exploit learning and auto-differentiation in molecular simulations. And my first example is something that's popped up a couple of times, this idea of interatomic potentials. Right? So in interatomic potentials, it's this key element of molecular dynamics simulations. And again, if Grant talked about this yesterday, but to make sure that we're all on the same page, molecular dynamics is a way to sample from the Boltzmann distribution, right? It's the most trustworthy way that we have to sample from the Boltzmann distribution at the atomic scale. And we do that by literally moving atoms forward in time following Newtonian equations of motion, right? That's literally what we do. And because we're moving atoms, we get to simulate sort of very, very, very tiny pieces of matter. And we saw some, what was injectosome. That kind of, the injectosome that we saw yesterday, that's kind of very big for molecular dynamics. That's the sort of thing that is almost outside of the scope of what you could do with MD. Plus, we interrogate the world in order to conserve energy and sort of really follow rigorously the dynamics. We need to move in about 1 to 5 femtosecond time steps, meaning that anything that is sort of a time scale that matters requires millions and billions of calls, or trillions of calls if we are at the issue of research, to this energy function. And then what's the energy function that describes the interactions between these particles? So all these things have been a ripe field for machine learning tools in molecular simulation. As you can think about coarse-graining to move fewer particles around. You can think about enhanced sampling techniques that allow you to draw more uncorrelated samples rather than, if you imagine you're moving 1 femtosecond at a time, your samples take a long time to decorrelate, right? So sure, in the infinite limit, you're drawing from the Boltzmann distribution, but instantaneously you're having sort of these highly correlated samples. So how do we draw more uncorrelated samples? Or how do we get the fastest possible interaction potential between particles? And that's what I mean by machine learning potentials. These are typically fit from the bottom up. You could totally fit them from the top down. So you could take experimental data and through either differentiation or trial and error, find the parametrization of a force field that reproduces experiments. And this is how this has been done historically very often, particularly for long-range interactions and sort of the forces that keep matter together, Lennard Jones, or dispersion forces that have typically been fit to densities and boiling points and things like that. And then the machine learning community and the machine learning tools have taken this task on from the bottom up, right? So essentially we get energies and forces from quantum chemistry. And what level of quantum chemistry could occupy sort of whole workshops? As in principle, we could do very, very expensive, very accurate quantum chemistry, but then that doesn't produce enough data. So we end up with some middle ground. And in solids, it's something called DFT-PBE, which is OK, but it's kind of not amazing. So everything for solids is fit on a ground truth that has its own flaws. But that's sort of swept under the rug for now on. And then sort of this is the first derivative that shows up. This is obvious, right? But it turns out this is how we get energy preserving force fields, which is critical, right? As I say, we're going to call this thing for 1 billion times. It needs to preserve energy. So typically, force fields are fit as energy functions, typically with like a per atom partition of the energy. So it's size extensive. So the total energy of the system is a sum of a per atom energies, which is a partitioning, but it's not necessarily how nature does it. And then our forces, we're going to get through auto-differentiation typically of this conserved energy to make sure that we conserve energy. And then we typically do force matching. We typically define a loss function where between the model forces and the quantum chemistry forces, and through a stochastic gradient descent with a big data set, parameterize whatever functional form we have. And that would be the second obvious derivative that we need to do stochastic gradient descent to fit our. Yes?
Can I ask you a question about this? I haven't thought much about these force fields, but what's the input to the force field? Like the whole state of the molecular cloud?
Yes.
Like a single particle state that goes in.
So it's the positions of all the particles in your system. At train time, it will be smaller systems that are inference time, because our ground truth has kind of cubic scaling, more or less, meaning that we typically can get training data in the hundreds of atoms, and at inference, we can go to sort of millions of atoms, depending on sort of the memory that fits. But the input to this is the Cartesian coordinates and atomic numbers of a bunch of atoms, of whatever set of atoms you're interested in. And there's typically some distance cutoff of the perception of how much the state of this atom needs to consider the states of its surroundings, right? Which takes me to this. I mean, I don't know if Tess is in the room or not, but after Tess introduced equivariant networks on Monday, it doesn't make a lot of sense to me. Just say the neural network architecture that kind of has achieved the most accuracy and the best use of data, so the most efficient scaling, are graph neural networks and equivariant neural networks. There are cheaper architectures that are easier to call, that are competitive in that sense, that may be easier to call, maybe cheaper to call, or need less data for training. But typically, sort of this message passing paradigm has been what powers these machine learning potentials. So, you know, in what is this, 2021, we get all excited. Ken Houck from UCLA has used like 1 million DFT calls to study how this reaction runs. These are, if those molecules look ugly to you, it's because they're objectively ugly. It's not just, these are like really tough molecules doing a complicated chemical reaction that sort of requires free energy tools, requires MD for sampling, right? So these folks in 2019 spent like, 500,000 DFT calculations in understanding the path by which these two reactions, these two reactants go through a bifurcating channel, and depending on sort of the trajectory that they come into the channel, into the reaction channel, they can sort of bifurcate into two different products. This is like a hard case. We're like, okay, these machine learning potentials can reproduce potential energy surfaces. Let's give this thing a shot. So we already know what this path kind of looks like. So we start from this transition state. We get data from the channel on the left and going right. We train a machine learning model. We look at the held out data sets. Like, yeah, this looks good. 1 kcal per mole per Armstrong. This is what people call chemical accuracy. This is like good. This model should be operating well. And then we go do we go do MD with that model, and it turns out of distribution in the regions that the models visit when it uses that inference, somewhat autoregressively. The analogy would be sort of you're sampling autoregressively, right? Because you call the model, you update the positions, and then call the model again, get the forces again, update the positions. So in that sense, it would be reminiscent of doing something autoregressively. And it goes to like cuckoo territory where the error is sort of 30 times more than is acceptable. Well, okay, we'll get some of these frames, put them back in the oracle, redo our train test splits, try again. It's like, whoa, we're getting very good. We're still horrible. And by the end of the 5th, 6th generation of iterations, this thing finally works. All of this was 1,000 DFT calls per generation, so it was still like a fraction of what the original study would have cost, right? So we really did get the acceleration. But I think for us, it's been pervasive that the machine learning potentials don't generalize well, and we're kind of doing MD to sample phase space that we didn't know in the first place, because if we knew it, we would already know the statistics of the system we care about. So this has been something that has happened to us every time. This is sort of a battery system of how lithium interacts. This is a class of materials that may be useful for batteries that don't catch fire, trying to make polymers that solvate lithium. And same story, the training data plotted against the phase space of the Boltzmann distribution at the end, when everything is self-consistent, it just had big patches that the simulation would eventually visit. And we found ourselves in this sort of chicken and egg situation most of the time we've used machine learning potentials. Yes?
I was just going to ask, what is the actual active learning algorithm that you use? Is it just some sampling?
Yeah, it's so I'm going to spend like 25 minutes talking about that. But yeah, we've moved on from unsampling to the sort of Gaussian mixture model of the latent space distribution that Boris Kosinski put out about a couple of years ago. But the whole premise of how do we do this in a way that is not just doing production simulations every time, getting a few of those points, retraining, doing another production simulation, getting a few points until things converge is the whole premise of what we need to move away from this.
I didn't quite get something you said, which is, maybe I can just rephrase it. You set up your conditions for an experiment, and then the conditions, and then the simulation evolves, and then what you're plotting there is a representation of the final answer, and you don't know the coverage of that final answer.
Exactly, exactly is that. So this is a long molecular dynamics trajectory on a potential that has been trained in a self-consistent way over that phase space. So we know the potential represents the phase space the simulation visits. But these two things, the training data that you have does not come from the Boltzmann distribution. It comes from whatever database somebody compiled. You on your own were able to sort of fill in spot by spot. And then, Zach is there, right? This general purpose relaxation force field. So there is a lot of quantum chemistry data of structures relaxing from an okay guess to the local minima by gradient descent. And that data is available, including for surfaces, for bulk. So these relaxation potentials are generally looking good. They're generally stable. They're generalizable. So over the last couple of years, I think relaxing structures is something that potentials can do in a trustworthy way. Rare events, barriers, things that are sort of going uphill to find a barrier, those are still very, very hard because they're out of distribution. And then I don't have a solution. I just have a shout out. Having good energies and good forces is a necessary condition, but it's not sufficient, as we just saw in my sort of first attempt at doing this. It seems that forces on held-out systems may be okay, but at the end of the day, the proof is in the pudding. And the pudding, we kind of need to do dynamics and recover the statistics. But we haven't really been able, as a community, to come up with sort of a universal set of benchmarks of how does the potential, how do these potentials actually do when you try to use them in production and to compare. I don't know, this came up maybe in conversation. Somebody asked me how these non-energy conserving potentials operate, because that would save you one derivative, right? If you just if you were to just fit forces and ignore the fact that they're the gradients of conserved energy, one of these catastrophic ones, I think, is the pot that is really bad. Does that. So it has been tried to save people one of these derivatives, but it hasn't worked in practice just yet. So going exactly to Grant's points, like how have we thought about active learning here? So there's two classes of problems. One is how you're going to do uncertainty quantification, and then how you're going to do sampling. Uncertainty quantification, we've spent some cycles, and ensembles works best. They're still uncalibrated. This has come up before. They're not very well calibrated, but they're reasonably smooth, and sort of they're reasonably predictive of model error. This mean variance estimation has no real reason for working, because this should estimate aleatoric uncertainty, which we don't have in quantum. Our ground truth has numerical precision, right? You take the same atom positions, put them into the quantum mechanics again, you should get the same answer with sort of machine precision, right? 10 to the minus 14 error. So this is made to capture aleatoric uncertainty. This is a generalization. Evidential regression is a generalization of the idea of mean variance estimation to estimate both sort of a distribution over Gaussians that should be able to estimate epistemic and aleatoric uncertainty. It looks sort of cool for molecules. We've tried to use it, and it's sort of not as effective. There is also a fitted parameter that sits in a denominator that has a tendency to go to 0 and blow things up. And then this is the last thing I mentioned earlier. So this is fitting a Gaussian mixture model to the latent representation of all your data. And then that can, in principle, give you likelihoods for the new data on the basis of all data you've seen so far.
So how many neural nets in your ensemble?
That's a good question. So people that do this correctly do 25, 30. We can definitely not afford that. So typically it's 5, 7. So these are very, very small ensembles compared to what they should be.
I was going to make an observation, but I think you're saying also fit a Gaussian mixture model.
Yes,
But
but yeah.
Gaussian, but I guess that you can't do a Gaussian mixture model if you only have 5.
Yeah, exactly. So I think it's one of those places where the pragmatism, I'm going to say cheapness, but maybe pragmatism of having a small ensemble sort of goes against the best perceived practices.
Roughly, what's the size of the data that you're fitting?
That's a great question. So I think the biggest you can possibly get, so with the 200 million that you folks have out, right? Which are maybe on average 200 correlated samples for 1 million different materials would be like a fair average. Yeah. So I would say as the biggest that's out there is about for surfaces, 200 million, which are actually 100 million materials and 200 correlated samples for each. This is for surfaces. For bulk materials, there is a similar sort of 100-ish correlated sample for 100,000-ish materials. So in general, it's a kind of a lot of frames. There's millions of frames. It's hundreds of thousands of chemistries, which is not that much. And then they're typically smaller than the things you would do inference on.
And you're doing additional DFT calculations.
And then exactly. So this would be the biggest you can possibly get, trying to make these universal relaxation potentials. If you're making this ad hoc for a particular system, thousands is typically enough for the particular phase space. If you really know what phase space you're going to be at, 1,000, 5,000 draws from the Boltzmann distribution are typically enough to train a potential for that particular system, right? So if you want universal, it's in the millions. If you want sort of ad hoc, it's in the thousands, as long as there's no distribution shift. If there is distribution shift, you could have hundreds of thousands, and still when you try to do something, move out of distribution, it's a catastrophe. So this is all these measures of uncertainty. So the various uncertainties versus error. I don't know. I know this looks very bad, right? Like this. I don't know what this is bimodal. RMD17 these are long trajectories for molecules with 17 atoms. So there's molecules that are not tiny. They're not big, but they're not tiny, and they're long trajectories that in principle should be converged. I don't know. I can spend all the time here describing, but you can see like nothing is particularly good. And these at least are very, very smooth, which will be very handy when I introduce the next thing. So this is my next gradient. And you know, the adversarial folks have thought about this type of thing for a long time, but I think in the molecular simulation side, they hadn't really been done, which is if we've got uncertainty estimates, instead of doing production simulations, you know, try to navigate all phase space and grab uncertain points after, we can actually do adversarial attacks on uncertainty or gradient ascent on uncertainty. And in that case, the Gaussian mixture models have very, very smooth derivatives, so they give you sort of these more stable paths for adversarial attacks. So this is exactly what we did. The first example with ensembles, right? An ensemble is literally, the difference between the standard deviation between all the members of the ensemble and the mean of the ensemble, and the signal of this gradient. So the signal in the derivative of this ensemble uncertainty, which is a differentiable operation, is typically enough to sort of explore phase space. So in this double well system, we start on one well, fit a bunch of potentials, and just by the sake of uncertainty, sort of the exploration following the gradient of this creeps up of the well and eventually finds the other one. And before anybody asks, the other thing you need to do is somehow try to stay in high likelihood phase space, which we do by constructing this sort of estimate of the likelihood of new points based on all the points I've visited plus the energies, right? I have an oracle for energies. It's imperfect, but I have an oracle for energies, and I have a build-up towards the Boltzmann distribution as I've been visiting, right? So I can estimate the likelihood of new points. I can estimate the uncertainty of new points and follow this gradient up. So this has become one of the things we do in order to get these potentials to operate. Yeah.
On the left, you're doing pure exploration. You're not trying to.
Yes.
And on the right, I didn't quite get it. Are you adding in something that's now doing exploitation as well?
Yeah. So this would be exploration in the sense that it just wants to maximize uncertainty without any attention to the likelihood of that frame, And this is literally the likelihood estimated by, this is the likelihood of the frame, and we can estimate the denominator, the partition function, based on all the points we've seen so far. It's not the true partition function. Exactly, and then we make the product of them. We've got a temperature here that is sort of the knob of this balance, literally, right? If you put this at 0 Kelvin, it really doesn't want to explode at all. And if you put this at very high temperature, it kind of ignores the probability part and it just follows the Yeah, that would be. It's not clear. I mean, let me. What are we doing? Maximizing uncertainty while likelihood. This would be maybe Thomson sampling. I think this would be more in the space of some Thomson sampling than maybe.
Is it accurate to interpret what you're doing as minimizing the KL divergence between the true Boltzmann distribution and whatever it is that you end up sampling?
I think maybe implicitly and in a hacky way, if we have my next sort of block is maybe a more direct attempt of doing that. But yes, I think implicitly, I think you're 100% on point. I think at the end of the day, what we're trying to have is match the Boltzmann distribution from our energies with the distribution that we've observed from the likelihood. So you're 100% on point.
I'm a little unclear what delta is. So delta is just like the indices of coordinates from your sample.
It's the displacement. It's the wait.
So the maximization you're doing over delta is to select out points from the data set, or you're finding new ones?
Yeah, so we do both, right? This is a whole chicken and egg, right? And maybe it relates to the question about sampling. Typically, we cannot do an acquisition function in the sense of evaluating what point in hypothetical space has the highest acquisition function. We're doing a local version of that, because if we had access to all of phase space, we wouldn't be doing this in the first place, right? So we need some local metric that allows us to find the edges of uncertainty, right? So we locally increase uncertainty, but we're not finding the global, right? This is not a global optimization technique.
Maximizes their acquisition function anyway. They just pretend.
Yeah, but typically you feel like you have a roster of all the things, like you have a grid of all the things you could try, and I think in our attempts at Bayesian optimization, typically we're in a place where we have sort of a grid of all the things we could try, and this is completely untractable. So it's just a gradient-based escape from the local minimum.
Maybe just to add in, like it's trivial to make these things intractable to converge. Like if you overlap two atoms or you do really bad things, like you can just get to parts of the phase space where like you will not get an answer. Like the simulation will crash. You'll have numerical instabilities. Like it's so easy to venture in there that you have to have guardrails like this. Like as soon as you start running the ground truth, it's really, really, really easy to mess up.
But there are points that are, yeah. There are points that don't have a ground truth. We cannot even label, because the oracle doesn't work for them. And then there are points that have very, very low likelihoods, but you could still bump into them. So somehow you need to both clamp that the thing will even converge and that they have some likelihood.
A priori, the phase space is unbounded.
Yeah. I mean, yes, yeah, because it's Cartesian coordinates times the number of particles you have, right? So it's essentially, yeah. Yeah, I don't know if anybody cares, but this is a couple of examples of specific things. So this is a material for that's been proposed for batteries. Lithium moves around in it, and by moving around, I mean it hops between empty sites to empty sites. And by hopping, I mean a rare event, because it stays in one minima for a while, goes over the barrier, stays in the other minima for a while. This is sort of thing that pre-trained potentials are not good for, because there's a barrier, and there's no reason why there would be barriers in the training data, right? So typically, you would need to retrain or fine-tune the pre-trained potentials. So the red points was what people were able to afford with the pure DFT oracle, and this is the diffusivity, the thing you care about, versus temperature. And the slope was fine. These black points are the experiments, but somehow there is an order of magnitude different. And it's like, well, is DFT wrong? What's happening? Because the experiments go up to 200 degrees less than people could afford simulations with the ground truth, with the oracle. So we come in, we fit, with points from this part of the world, we fit a machine learning potential. We go sample with the machine learning potential, we're able to do, 3 orders of magnitude. We can see 3 orders of magnitude more time scale than people originally could. And it turns out there's a phase transition where instead of all the atoms moving like a liquid, only one direction, one channel remains mobile, and the other one has a slightly higher barrier and freezes in, right? So it turns out everybody was right. It's just that they were missing sort of the middle point. So this is like a clear, the 3 orders of magnitude were the thing that was missing to relate experiments and theory. This is another recent one. Instead of doing molecular dynamics here, we're doing grand canonical sampling. So we're sampling with Markov chain Monte Carlo in the grand canonical ensemble, meaning that we can sort of create and destroy atoms. This is something we used for surface reconstruction, right? The surfaces of materials, as they're exposed to whatever they exist against, could be solvent, could be gases, they will reconstruct, right? The surface of materials are not exactly pristine cuts of the bulk of the material, right? The atoms move, maybe they oxidize, maybe they reduce, maybe they enrich in some elements, maybe they get poured in other elements. So again, these are 6 generations of various tools. This is adversarial attacks. This is just sampling with MCMC and grabbing some frames. This is a machine learning potential when they work. And we end up finding the right experimentally confirmed reconstructions, right? So under strong chemical potential for titanium, right? There is a double titanium surface reconstruction, a single layer titanium oxide, or a single layer strontium oxide. So these are sort of 2 examples of 2 things that are out of distribution for the pre-trained potentials, but once you've got a potential that's trustworthy, they're typically tractable. And then this is the last one. This just got accepted. This is literally attribution in the most classical way, right? So this gradient I just described earlier, we will follow the gradients to distort the system, to move the system and send it to the oracle. Here we're doing production simulations and attributing model uncertainty to whatever atoms are responsible for global uncertainty. And this is important because, as I said, the size of the box at inference is much larger than what fits in the oracle. So at some point, we cannot put these whole large boxes in the oracle, but we can definitely carve out the little regions that require relabeling, right? So this is a way of doing that. And my last, if this runs, I mean, we got derivatives. This is another one, right? We can do Hessians and find the normal modes of uncertainty. And this is a water box, a reactive water box. I don't know if we were talking about water potentials the other day. I don't know if folks have reactive potentials. We have a reactive water potential. And the most uncertain, sort of the normal mode of uncertainty, the first eigenvector of uncertainty is this Grotthaus mechanism of all the protons moving in sync, right? Which is, it's a known phenomenon, right? This is something that happens. This is how protons move in water. Every water sends sort of a hydrogen bond to the one next to it, and you have this chain of protons moving in the liquid. Yeah, I mean, you can do ring. We've done ring polymer MD with this. Maybe we made the rings were too small. It didn't sort of nail down the shift in vibrations, but it was different from. So it moved a little bit with respect to classical MD. So with this you can afford, for small boxes, we can afford nuclear quantum effects. But this is just the correlated motion of all these protons that turns to be an eigenmode of uncertainty. Because of course all these events are highly correlated and rare, so they're not really expressed in the training data. Yeah. No, I mean, this is just a thing that we did once and to see if it could help and sort of to see. But in practice, it's kind of a pain in the neck, right? This is a Jacobian vector product, so we need to sort of do the Hessian row by row. So it's not particularly efficient. So no, this we've done it just for kicks. And this technique exactly to Ji-sung's point, right? Like, how do we think a bit more sort of sampling-wise about the mismatch between the Boltzmann distribution based on the energy Boltzmann and the likelihoods that we're seeing. So I think this is, in essence, what this method does. There's essentially a set of techniques that are called enhanced sampling. Sorry, I flipped the slide, so maybe this is not the easiest expression. But essentially, there is a class of techniques that are called enhanced sampling, which is you do molecular dynamics following trying to draw from the Boltzmann distribution, plus some bias term. And this bias term you add to force the system to visit rare events across a dimension that you already predefined. Right? So there's this collective variable or a reaction path that you predefine as the dimension you care about, and somehow you add bias to explore that dimension, right? In that case, the dimension we're going to explore is literally the uncertainty, right? So we're going to bias the system to move during a stable simulation to go visit uncertain regions. So instead of doing gradient descent, we're doing sampling, right? So maybe it relates back to the locality versus exploration part we were just discussing. So this is our first attempt at doing literally that. We train on this sort of, alanine dipeptide is like the NIST maybe of enhanced sampling. This is how the sort of relationship between these angles and likelihoods would look like. We do a very high temperature trajectory to see lots of phase space. We show a tiny, tiny, tiny amount of that trajectory to the model, and we bootstrap one of these where we start with the sort of little phase space we've seen here, draw MD, and force it to explore based on the negative log likelihood of the point. So again, I don't think we're doing exactly the Clay divergence explicitly because we're constructing these distributions on the fly. It's not like we have them statically. It's that we're moving 1 femtosecond at a time and sort of resetting the distributions generation by generation. But I think if we formally explored it, I don't think we would be far off from doing something like what you described. And yeah, this kind of works. So this generation 1, it doesn't even know where the other sort of high likelihood regions are. It just knows about sort of this high likelihood region. And a couple of generations, it's kind of bootstrapped all the phase space that matters for this system. This is the part that I maybe sort of we haven't really explored well in this paper, which is we came to this as an active learning idea. It's like I want to make my potential better, and we've commingled that with I want to make my sampling better, right? But I want to see points that are outside of distribution versus I want to see points that are outside my training data set, right? So I think this has legs beyond the machine learning potential training and all the way to just an exploration CV. It's literally, right? It's literally the mismatch between the evidence-based samples that I have and the energy-based samples that I get from molecular dynamics. And it's Q2, so I'm going to skip the CV. I can come back to this. But I wanted to make sure I have some time to talk about alchemy, which is going to be my last gradient. So it's the derivative of property with respect to elements, right? So I want to change elements, which are a very, very discrete variable. But it turns out these machine learning potentials, these pre-trained machine learning potentials are so smooth that they have allowed us to do something that I thought, on the one hand, is a little bit obvious because the idea has existed for a long time, but it hadn't really been done on neural network potentials. And this is the idea of alchemical simulations. Alchemical simulations are essentially thermodynamic integration. So they provide, you can never get absolute free energies of almost anything, right? It's typically untractable. But with thermodynamic integration, you can get the difference in free energy between an initial and a final state if you can somehow trace a continuous path to simulate between them. So in alchemical simulations, this is sort of through unphysical intermediates. So in our particular case, it's going to be through alchemical atoms, which are sort of atoms that are a superposition or a mean between two existing elements. So imagine you could understand the free energy difference between sodium chloride and potassium chloride by integrating a path that starts at 0% sodium atoms and slowly mixing the Hamiltonian of sodium atoms with the Hamiltonian of potassium atoms. This is free energy perturbation. This is what literally free energy perturbation people do this for ligand-protein binding affinities. It's just that it hasn't really been sort of a good hook to do this in materials. So yes, of course.
And then along your simulation path, you can compute these free energy differences. But if you would compute the final free energy, this would be again hard. So that's the idea? Or?
So it's both. You can do this from a tractable system to an intractable system, or sort of an analytical system to a system that you don't have an analytical free energy for, in which case you would have an absolute free energy because this one was tractable, and you've integrated your path to the hard one. So this one plus the difference will get you the absolute free energy for this guy. But even then, if this one is untractable on its own and this one is untractable on its own, you can still get the delta between them by integrating between both of them, even though both of them are you don't know where they sit. You can know where they sit relative to one another.
Is that again related to the Jasinski?
Yeah, it's coming. We've got some non-equilibrium. So one way of estimating this is with irreversible path left to right, right to left, and taking the mean, which is literally what we did in the slide.
But yes, the adiabatic limit. So you do it slowly, and there's no dissipation.
Exactly. So if you can do it. That's fair.
Can I ask a quick clarification?
Yes.
So when you're changing atoms, what does that actually mean in the force field?
Yes. So all this graph or message passing neural networks operate more or less in the same way. Atoms send each other messages that are a function of my state, my neighbor's state, and the features of the edge between us, which are typically distance and maybe orientation in equivariant models, right? So, and then atoms will have a state that is a combination of whatever message they receive and the old state they were in, right? This is how these methods more or less operate. So what we're going to do is to make the alchemical atoms, receive regular messages and pass scale-down messages, right? So what used to be a regular atom, we're going to split it into two non-interacting alchemical atoms, right? So imagine that the cation we're going to split in a sodium and a potassium. And then in the message passing operation, sodium is going to send 10% of the message it would have sent, and potassium is going to send 90% of the message it would have sent based on their environment, right? They themselves don't see each other. So it's not dissimilar to the way people sort of couple classical alchemical methods by shutting down the Hamiltonian. In this case, sort of we're interpolating over messages. That turns out to be way more efficient. You could do this scaling down the states. And I think some people had tried this in conversations. People have told me, well, we tried this doing the superposed atoms had average states. And that turns out not to work very well. It's much better for these atoms to have the full sodium or the full potassium state and just send scale down messages. Does that?
Yeah. And I think maybe one other clarification is when you're actually doing the MD, there's no notion of the actual atom identity because it's just the forces or energies force field. So could you just interpolate whatever the parameters are for your charges or?
Well, that's the thing. There's no charges. The only source of energy or forces is the per atom partition of the energy, right? These machine learning potentials partition energy as per atom contribution. So all the many body heavy lifting is done by message passing. But at the end of the day, the energy is a per site scalar and a sum of per site scalars. So in that sense, yeah, all of that sort of all of these sort of subtleties about what to tune down at what point goes away because I just need to scale down the messages and everything sort of naturally behaves. So there's two things we can do for this. One is rigorously correct, or it's literally what Grant was saying. We can get alchemical free energies, right? So this would be the free energy difference between an initial and a final state. And typically, we're in this instance, instead of being very slow, we do sort of the mean of the irreversible work on the path left, forward, and backwards. And that gives us a good estimate of the free energy difference between the states. So we compare with Frenkel lab, which would be the traditional way of doing it, starting from an Einstein crystal, what you said, right? What Stefan said, start from a perfectly known system and couple in from a tractable toy system and couple in the Hamiltonian, and then couple it for the system with the vacancy, the system without the vacancy, or the alchemical transformation. You can see the two agree. They give you the same, fortunately, right? Because the Frenkel lab is rigorously correct. But we get much better, with the same number of samples, we get much better averages precisely for this, because we were taking a path that is much shorter in terms of interpolation, right? We're interpolating states that are very similar instead of going from a completely decoupled to a completely coupled Hamiltonian. And then this is delta G between phases. So this is what is the difference in free energy of doping this perovskite. So this cesium-lead iodide, and this is cesium tin iodide. What is the delta G? So same idea of comparing what is the difference in free energy of phase transformation between these two phases for these two compositions, right? So we can construct thermodynamic integration pathways that are much shorter than the brute force that you would get from a Frenkel lab. Right? So again, this is the difference between the true answer for the alchemical simulation and for sort of Frenkel lab simulations for either of them. So we just get much better averages. This is sort of more or less expected. And then this is the part I'm really excited, and the students like, Rafa, but there's no reason why this should work. And it's chemical disorder is a big issue for material simulations. Chemical disorder means that oftentimes you can have a material that has a single crystal, a big crystal, where the atoms are randomly distributed between lattice sites, right? So the crystal is the same for everybody. It's the same actual geometry, but the atoms are distributed at random, right? These are called solid solutions. I don't know if you heard about the A-Lab paper, a Nature paper out of Berkeley and Google end of last year, where a robot made 70 new materials, but maybe it made none because of this. Because actually all the materials they made, or the majority of the materials they made, were disordered versions of materials that were known. So disorder is a big deal. Like I said, entropy favors disorder, obviously. So unless there is sort of an energetic driving force, same composition could be distributed in this sort of disordered fashion. So it turns out that the alchemical atoms do a good job at representing infinite disorder. So actually a 2080 mixture of sodium and potassium behaves on average like a random infinitely large disorder system that is made of 20% sodium and 80% potassium at random. There is a linear observation, there is sort of a 1950s observation that solid solutions tend to be a linear combination of the endpoints, right? That the 50-50 alloy has properties that are halfway between the endpoints. That's called Vegar's law. It's not a law, right? It's just an observation. But there are lots of things that break Vegar's law. So on the top, this is for two different systems, right? So Syria, this is disordered alloys of, or disordered solutions of tin or zirconium in Syria, and then the tin could be anywhere, and the properties, the size of the unit cell gets smaller and smaller the more you dope with tin or with zirconium, but not in a linear fashion, right? This is experiment. You can see there is a big kink. We don't quite get the kink, but it turns out with a 1 by 1 by 1 tiny unit cell, the alchemical atoms somehow or do capture the non-linear effects, right? This would be the linear interpolation. So zirconium behaves linearly, both in experiments and in the alchemy. But the doping with tin behaves sort of in this non-linear fashion where you don't get an interpolated version of the endpoints. This is a different system. This is bismuth sulfide halides doped with 2 elements, so there's sort of more averages. But it's the same, right? Like some of them are sort of okay linear interpolation between the endpoints, but then the blue, which is the chloride iodide, one is bigger and one smaller, right? It's the behavior with doping is not a linear interpolation between the endpoints. And the alchemical simulations on with these pre-trained potentials do capture that, which is, I think, something that was unexpected, in addition to sort of the more rigorous unexpected free energy integration. So with this, I think I'm up to time. Really big shout out to the team and to you folks for sticking around. Thank you.
Thanks for the great talk. Quick question about, like sort of a broad question about active learning in general. So it seems to be, a de facto way of making these neural network potentials more robust and stable. How do you think that active learning is going to scale in the age of like universal force fields? We have these huge data sets with tons of different chemical systems. Is active learning still practical? Do we have to change the way we think about it? What are your thoughts on that?
Yeah, that's, I think these folks call it softening, which is, I think that the universal potentials have gone to a point where they're stable. The simulations don't blow up. Typically, historically, a very common behavior was when the models, when deep neural networks really don't know, they revert to the mean, and the mean of the training data is 0. So you would typically go uphill, uphill, uphill in energy to unknown regions that are rare. That's why they're higher in energy. At some point, the model would say, I don't know, this looks like the mean. And it would dump all that energy back into kinetic energy and explode. So this doesn't happen anymore. These models are stable, but they're way too soft on the transition. So when you start going uphill, at some point they say, you know what, I think this is plateauing, but it's not. It keeps going up. So there was a paper from folks here that have trained CHDNet, right, from Cedar Group, doing active learning against softening. And they find you don't need a lot of data to fix softening, right? You just need some data in the right part of phase space. So I think what I don't have an answer for is how do we do lifelong learning? The approach like fine-tuning is not a problem, but how do we do some lifelong learning? I don't know how to think about sort of the size of the generations of adding data to this. I don't have a good answer for that, but I know the premise of active learning, at least for a couple of years, till we patch all the possible holes of all the possible barriers we can care about, I think it's going to need some iterations. But I don't know how we do this sort of online rather than in big sort of releases every year.
So the reason you can't train large ensembles is because that loss function, fitting all the force. So the reason you can't train large ensembles is because the loss function of fitting all the force fields per atom is just a huge loss function. Is that right, or is it something else?
I think it's just the cost. I mean, at the end of the day, it's just the times the cost of the original model. So it has to do more with sort of the memory and so it's more about sort of resource constraints than fundamental sort of learning dynamics or you could totally train a large ensemble that would give you a smoother uncertainty. It would just be like a much clunkier thing. When you're going to backprop over uncertainty, you would need to load all the models in memory at the same time and sort of move, right? Like this variance means that you need to backprop over all the models at the same time. So you incur a big memory footprint.
How parallelizable are these DFT calculations?
The DFT badly. The neural networks are like, within the same paradigm as everybody else's. The DFT is hard to, I mean, people have made ad hoc codes that parallelize better, but have large pre-factors. So you end up paying 100 times more so that you can scale better. And that makes sense for 1 million. But again, that would give you a oracle that can access a large box. So you could sort of label a large box at the same time. But that may not be necessarily, if uncertainty is very local, maybe you want sort of 4 different pockets of uncertainty rather than running the oracle on a very large box. So I would say in terms of active learning, I don't think the scaling of the oracle is a huge issue.
Thank you very much. I have a question about the alloys.
Yeah.
So, so with the alloys, you have this linear effect.
Yeah.
But is there something you could envision for materials where substitution doesn't have a linear effect? I mean,
Yeah.
like add like, for example, strange metals or superconductors, where like substitution you tune to your new phase, for example. Like,
yeah.
like I guess like because here like everything is very mechanistic, I guess, right? Like if you tune the size, then the size of the tune itself changes. But what happens when you really exchange them? And like, could this also be useful for these systems maybe in the future? Or is this because you have correlated effects and everything is more complicated?
I mean, the fact that this has a big kink in experiments and we get a soft elbow, it's already a sign that, salient of delta functions that, 0.33 becomes a semiconductor and it goes away. I don't think that type of thing would be easy. Also, just electronic properties are much higher. This is all energies and forces, right? I think electronic properties are much higher. So I would say in principle, why not? In practice, there is very little work on electronic properties of ML for electronic properties because these energies and forces are okay. Electronic properties with PBE are just not very good. So there's not that much ML there. And then these singular behaviors, I don't know. I mean, I think we would get the elbow, we would get this, right? Like where we would see it show up earlier. We get some hysteresis, right? So I think it would show up earlier, disappear late, and be less salient, right? But we might be able, I don't know, best case scenario, I think it would look a little bit like that example, where maybe the behavior shows up, but it's less singular than it would be.
Something like a superconductor.
Thanks.
Thank you.